Looking at a game programming syllabus can feel like staring at a giant wall of math. It's dense and heavy, but if we let those equations collapse into something familiar, we find ourselves in a normal, everyday living room. This room is the key to understanding the course. Every line of code in game development is simply an attempt to mimic the physical world inside a computer. When you turn on a computer, it's like looking at an empty plot of land. To build something there, you could manufacture your own hammers and saws, or you could walk into a fully stocked workshop. In this field, we call that workshop a game engine. This diagram shows the two types of workshops you'll use. On the left is Pygame, which works like a flat 2D drafting table. On the right is Unity, which operates like a deep 3D mechanized assembly line. These engines exist so you don't have to write the laws of gravity or light from scratch. They provide the basic rules of the universe so you can focus on building the game. To make this digital room feel lived in, we have to move things around. Whether you are sliding a chair or spinning a table, your computer views these as geometric shifts, known as transformations. In this diagram, we see the three main moves. Sliding a chair across the floor is translation, spinning it on its legs is rotation, and changing its size is scaling. Once the furniture is in place, we need to see it. We use color mixing systems and lighting logic to simulate how a flashlight would bounce off these walls. This allows the computer to understand which surfaces are bright and which are in shadow. To show all that math on your monitor, the computer takes a final snapshot of the calculations. This step is called rendering. It flattens the 3D room into the single colored image you see on your screen. Graphics programming is essentially a list of instructions. You are telling the computer exactly how to draw a flat picture that feels like a three-dimensional space. A world that looks real also needs to act real. Without specific rules for how things touch, our digital objects would just be ghosts that pass through each other. Look at what happens when this apple falls through a wooden table. To fix this, we write solid object math, or collision detection. It's the digital equivalent of the physical resistance you feel when you stub your toe on a table leg. To make that apple bounce or fall at the right speed, we use physics calculations. Think about the way a phone drops or the way you jump. The engine uses these formulas to simulate weight and momentum. These physical rules keep the world from feeling hollow. Without them, your character wouldn't walk on the floor. They would simply fall through the bottom of the map. Realistic rules are a great start, but a game also needs to be fun. This is where the developer becomes a referee, adjusting the rules to create a fair challenge. If you played basketball with a hoop that was 100 feet tall, you'd give up in minutes. But if the hoop was only 2 feet tall, you'd get bored almost immediately. As this scale shows, developers are constantly sliding the weights between frustration and boredom. We call this game balancing. It's the process of tuning enemy strength and player speed to find that perfect middle ground. When a game is balanced, the player stays focused and excited. They feel challenged enough to keep going, rather than quitting out of annoyance. Even a perfectly balanced room can feel empty. To populate the world, we add computer-controlled characters that can react to your every move. These characters don't have actual brains. They follow simple if this, then that logic trees. It is the same thought process you use when playing tag. If the person who is it gets close, then you run the other way. Those characters need to know how to navigate around the furniture we placed earlier. They must find a way from point A to point B without walking into a wall. This grid shows a navigation system called A-Star, the same math that powers Google Maps. When a path is blocked by a red barrier, the calculation instantly finds the shortest possible route to the finish line. By combining these logic trees with route-finding math, we create digital opponents that seem to think and react to the choices you make. The final layer of the world is sound. Just like a movie soundtrack swells when things get exciting, audio integration provides the emotional cues that tell the player how to feel. When we combine the art, the solid physics, the AI logic, and the sound, we complete the game development lifecycle. It is the total journey from a single core idea to a finished product. On a smartphone, this process is even tighter. This diagram shows the constant struggle to keep a game running smoothly without draining the battery or running out of memory.
Every single concept we've covered, from lighting to route finding, works seamlessly together to create the experience you see on the screen. A computer sees the world as a series of translations. Once you see the connection between a physical coffee cup and the wireframe model on your screen, you've grasped the core of the subject. Every digital world starts as a list of instructions based on things you already understand. When you view math as a description of a bouncing apple or a game of tag, the complex equations on your exam start to feel like common sense.